Sometimes you might find that to prove something in real analysis, the best approach is to essentially divide and conquer. So this is what you would call a proof by cases or an exhaustive proof. You do a proof by cases when you can break up every possible application of the theorem into several different scenarios and then prove each of those scenarios one by one. So let's look at a very famous inequality that comes up often in advanced calculus. This is called the triangle inequality. What the triangle inequality says is that for any real numbers a and b, the absolute value of the sum a plus b is less than or equal to the sum of the individual absolute values, absolute value of a plus absolute value of b. So the size of the sum is less than or equal to the sum of the sizes is one way you could think of that. You may wonder why this is called the triangle inequality. Let me sketch you a picture. It has to do with the shortest distance between any 2 points in the plane being a straight line rather than being the joining of 2 other line segments. So here's a triangle, and let me label the top 2 sides actually as vector lengths. So if I look at it this way, then the side on the left will be the length of the vector A going from that bottom blue point up to the end of its arrow, and then the top side will be vector b, and its length is the length of vector b. Using vector addition, that third side could be considered the vector sum of a plus b. Therefore, its length is the vector sum a plus b. Now, what the triangle inequality is saying is that the length of that third side is less than or equal to the sum of the lengths of the other 2 sides. In other words, the shortest route from the bottom left blue point to the top right blue point is to take that straight line. If you join any other 2 line segments, like the vectors a and b, then you'll end up with a longer route. So the straight line distance is the shortest distance between those 2 points. I've illustrated this triangle inequality with these vectors, but really it's just a statement about addition of any 2 real numbers. So what we're going to do to prove this by cases is to break up different scenarios based on whether or not a and b are positive or negative or 0. And the reason why we're going to do that is because the absolute value function depends on the sign of what's inside, right? So how do you take the absolute value? Well, if it's positive, you don't really do anything. If it's negative, you flip the sign. So let's consider ways to combine the signs of these individual elements. The first proof we're going to do has 3 different cases, and this is usually the first thing people attempt when they want to prove the triangle inequality. I'll show you a second, faster proof that only has 2 cases after we're done with the first proof. Okay, so for case 1, you might start by imagining that a and b are both positive. You can rope 0 into this case and say that suppose a and b are both non-negative. So they could be positive or 0, 1 or both could be 0. Well, what happens when you add 2 non-negative numbers? The result is non-negative. Now we can use the fact that the absolute value of a non-negative quantity is just the expression itself, right? You don't have to do anything to take the absolute value. So the absolute value of a plus b is just a plus b. And then since a and b are both non-negative, a is equivalent to the absolute value of a, and b is equivalent to the absolute value of b. So here we actually get equality rather than an inequality. For case 2, let's imagine that a and b are both negative. If you add 2 negative numbers, the result is a negative number. So a plus b will also be negative, which means to compute the absolute value of a plus b as a quantity, I want to flip its sign. So the absolute value of a plus b is a -1 times that quantity a plus b. Now distribute the negative. We have -a plus -b, but notice a and b are both negative, which means that when I negate each of them individually, that's actually equivalent to taking their absolute values. So once again, in case 2, we actually get equality. Inequality happens when they have opposite signs. So for our final case in this first version of the proof, suppose without loss of generality that a is positive and b is negative. Here it really is without loss of generality because we're doing addition, so it doesn't matter if I write a plus b or b plus a. So I can take a to be positive and b to be negative. What happens when I add them together? From the point of view of b, I'm adding to b a positive quantity. So that means a plus b will be a larger number than b on the number line. It's going to sit to the right of b on the number line. From the point of view of a, I'm taking a positive number a and adding to it a negative number b. That's like subtracting off of it, so that will sit to the left of a. Therefore, we can say that b is less than a plus b is less than a. At this point, I don't actually know if a plus b is positive or negative, but here's what we can say. The absolute value of a plus b will be less than or equal to at least one of those two individual absolute values. I'll sketch a picture in a second, but we'll say that it's less than or equal to the maximum of either the absolute value of a or the absolute value of b. In fact, it could be both, but it's less than or equal to at least one of those two. Both of those numbers are positive numbers, so if you take the absolute value of a and add to it the absolute value of b, you're going to increase the size. Ditto if you take the absolute value of b and add to it the absolute value of a. So whichever one of those two is maximal is less than or equal to the sum of both of them together, and that's our desired inequality. Here's a picture of what this last case is illustrating. Let me imagine this is the number line. Here's the number 0. B is going to be a small negative number. A will be a large positive number. If I do a plus b, I'm going to end up around here. That is a fairly large positive number, so when I compare the absolute values of the three quantities I have here, a and a plus b are actually equal to their own absolute values in this case. B would come over here. So in this particular case, the absolute value of a plus b is less than or equal to the absolute value of a, which is the maximum of the absolute values of a and b. You could sketch a similar picture where b is very negative, a is only slightly positive, and you would be able to say the absolute value of a plus b is less than or equal to the absolute value of b in that case. That third case might indicate to you that there should be a faster proof just based on the sign of a plus b rather than breaking it down in terms of a and b, and that's definitely the case. So first, let's suppose that a plus b is non-negative. So suppose a plus b is greater than or equal to 0, then the absolute value of a plus b is just equal to itself. Now here, a could be positive or negative, likewise b, we don't know the signs, but any number is always less than or equal to its own absolute value. Here we don't know if a is positive or negative, likewise we don't know the sign of b, but what we can say is that every number is less than or equal to its own absolute value. So a is less than or equal to the absolute value of a, and b is less than or equal to the absolute value of b. And then we have the inequality that we want. Similarly, if a plus b is negative, then the absolute value of a plus b is equivalent to just taking the quantity a plus b and multiplying it by -1. Distribute through, and now we're looking at the numbers negative a and negative b, which are less than or equal to their own absolute values. So you can see this is a much faster proof that takes the triangle inequality and improves it with only two cases.